this topic, and it's already about the real structure that can be implemented in practice. Structured diagram of an aerospace cognitive radar for the Earth remote sensing. And taking into account this structure of cognitive radar that has to implement adaptive transmitter, adaptive receiver, a dynamic database that is consists in model of the prediction, also adaptive antenna array and knowledge-aided processor, and maybe radar scheduler. Knowledge-aided processor can be realized on FPGA. And we have some continuous signals algorithm optimal and digital signal algorithm optimal. And when we came to real practical implementation of this radar, we understood that it's quite difficult to buy and to use digital antenna array. It costs a lot, and it has limitations on abroad transferring. And in Ukraine, we have some companies that is called Arion, and they develop radar with high frequency part from 10 GHz and up to 90 GHz. And some they create them and give. We can take signals already at intermediate frequency, and then using some analog to digital converters, try to convert the signals and to perform digital signal processes. So the idea is to take the high frequency part from continuous signal and exactly the filtering processing from digital signal. And we took some information from this algorithm and some information from this one, and created one algorithm of receiving a high frequency signal like observation equation, then processing it at high frequency with such part. And after we will get a process of nonlinear filtering already in discrete form. And here we will use some adaptive receiver that change parameters of filters according to signal to noise ratio, some predictions according to the models and dynamic database, and some also predictions of the errors. And on the basis of this such general algorithm and final result, it will be digital coherent image. And we did not do a lot of research on the model of our parameters that can change, and we think that the idea has to be with using information technologies. Some neural networks, maybe some other studying with teacher, without teacher, and other ones. So it has to be. But the idea of the previous century, it was just a description of signals through some through some transfer function. And for example, signal from low frequency filter, it's like RC filter. LC filter, such one. It's the process of it's the Markov process with one stage of it's a Markov process, or it's also called the process of Arnstein-Uhlenbeck. And using such a model of our parameter, we can create such function of prediction and the first derivation of this prediction. And using such approach, we developed such a structure of radar that consists of almost high frequency part. It's our antenna array, where we take information from every its element, have possibility to change amplitude and phase characteristics or time delay, then adding of the signals to many elements, and then matched filtering according to every distance. It has to be performed at high frequency. Usually in synthetic aperture radar, they performed at high frequency, and then only after it comes to analog to digital converter and taking into account bank of reference functions, we can create artificial aperture of the radar. And this already, its frequency almost like 3 kilohertz or maybe up to 10 kilohertz of pulse repetition period. And then after this aperture synthesizing, it starts the process of nonlinear filtering that can be implemented in discrete form using some FPGA, and also adaptive transmitter. But the main point that is not investigated in this in these papers, it's definition of this model of our parameter of the surface. So we propose take into account existed radar images, optical images, digital elevation model, take it all together, study some neural network, and use this function already here on new level of measurements. And then we will get structure of really cognitive radar with adaptive antenna array. The first part, sorry, with adaptive antenna array, adaptive transmitter, adaptive receiver. Here, this part, knowledge-aided processor. It's or intelligent processor. It's mentioned here that it has taken into account clock signal, surface observation model, then previous measured parameters, a priori values of our parameter, and other one. And then this intelligent processor controls transmitter, receiver, antenna pattern, and different functions. And okay, this is all almost main parts of cognitive radar. And we did some simulation of radar images. We decided to use such approach that is already existed. For example, if the scattered coefficient of the surface is small, then no need to send high power signal to that direction. Don't take that information. And if scattered coefficient of the surface is high, so it contains a lot of information about objects, then let's send in that direction higher energy level. This some approach to construction, one of approach to construction synthetic aperture to cognitive radar. And we have some algorithm for test radar images simulation. It was published in a lot of our previous work, and it was test SAR images like with high performance, the best quality in this problem statement. For example, it's airport, some airport in Kharkiv, not the main, but some of them. And we created here the classical synthetic aperture radar technology, this image. And this one was created using this cognition, like adapting energy of transmitted signal. If we have for example, in this part, we have low level of scattering, then no need to send a high power signal in this direction. And if we have here like high scattering model of the surface, let's send the higher energy, and we obtain these two images, and it's on your decision which one is better. But we used some metrics for image testing. It was mean square error, PSNR, structure similarity metrics, and three metrics with non-reference signals. In almost all of the results, our cognitive SAR image was better. And besides just this one, it showed the rows. This was the measuring of metrics with test image like self to self. So mean square error, the lower the better. We see that this one the lower. PSNR, the higher the better. We see that this one is better. As sim 1 is the best structure similarity, this one gives better result, and this was also like up to 3.8, the closer, this one is closer, and 33 points, this was also closer. Only this metric gave worse result. And we tried the other one more like different structure image. It's some bay or some city, and it gave us such results. And I can see that in this image it's already can be seen that quality is much better for such image. We can see here bridges. We can see that this here we have some streets, for example, and at this image it's not seen. And also this is can be described as some building because it has higher level of scattering and some okay, forget the word, and some backside of this building, and here it's nothing. So in this image we got much better result of cognitive radar application, and also all the metrics gave good results besides just this one. And in conclusion, we can say that if we have like homogeneous image, then our quality indicators increased by 7%. But if we have disparate structure of the image, our quality was increased by 35%. Thank you for your attention. Okay, Ivan, please. Ivan,
yes. Could I ask a small question? Have you got a comparison of both approaches, classical and cognitive SAR images, for object recognition or for blob analysis? Because after the getting image, we need to detect some objects, for example, buildings, cars, people, and other. Have you compared both results for some maybe algorithms, maybe some easy one for blob analysis? Okay, thank you.
Okay, thank you for your question. No, we didn't come to this stage. We only used these image metrics that are usually used for image quality analysis with reference signals and without with reference image and without reference image, non-reference metrics. Only these several metrics were applied and for analyzing the quality metrics. But thank you for your question. It may be the future work.
Okay, thank you too.
Okay, Tatiana Shmileva, please.
Yes, I hear, and I have a light, electrical problem, not. I have a question about your methods and cognitive system and advantages of cognitive system. For example, if application in drone for unmanned aircraft, may application your system and equipment of this system in drone for monitoring, for image, or disadvantages have. No, only advantages of this system.
Application of synthetic aperture radar to the drone, it has two sides. First of all, its advantage because of moving object. Because of this moving, we can create artificial antenna. But the other disadvantage that drone moves not linearly and with some changes of trajectory. So we should have system of stabilization and some feedback to adjust our it's called matched it's called I forgot this
No,
one
maybe combine.
signal for receiving forgot. So this part of processing, this one, it has to be adjusted because here we can v it's the speed of aircraft and r is distance to the surface. So through the feedback we should adjust this algorithm. So in general it's advantage, but implementation is quite difficult.
No, yes, thank you. Interesting, maybe application in future use
Yes.
drone or
Yes.
combine.
Mhm.
Thank
Okay,
you.
thank you. Okay, Ted Kochansky, please ask the questions.
Yes, very, very interesting presentation. I was wondering about how sensitive these algorithms are to issues with stability of the transmitter, because you need the things to be very precise.
Yes, it's also interesting question because on the one hand we have to change the parameter of transmitter, for example central frequency or the amount of energy, but on the other hand we know that object that devices that can easily change their characteristics, they are usually unstable, and that's why in this so great complex uh, I cannot answer to a question like precisely or accurate. I think that usually this
Just a second. In your simulations, did you introduce any?
no
No,
no I use transmitter with stable parameters.
stable. Yeah, yeah. Obviously, that's a challenge because
Yes.
the longer the duration of your uh, algorithm's collection of the data, the stability issue becomes more and more of a concern. If you have a very short uh, period of time, the stability will not be an issue. But then, of course, you don't get very much of an advantage over just a single pulse kind of a situation.
Okay, I can add that to this problem, such company like DLR, I think that it's Deutsche Laboratory of Radars. They
Mhm.
have such a radar as Tandem X, Terrasar X, and also system Sentinel. They have transponders on the surface, and they have corner reflectors for periodical calibration of their systems.
So that's very much of a cooperative target that you're going after. If it is, you're going somewhere, flying over the rainforest or something like that, and
Mhm.
you don't know what's on the ground below. So it's, yeah.
Yes.
not. And the other question is just, I don't want to monopolize the question, but have you thought about the integration with the work that people are doing now with LiDAR, with the RF and the optical, combining, particularly with something like going for these archaeological applications in rainforests or in other places where the could be cooperative, could be beneficial?
Really, we did not have such idea to apply this technology to LiDAR systems. Because of this coherent processing, we had some project with Switzerland, University of not university, yes, University of Basel in Switzerland, and we worked on applying this technology to OCT, optical coherence tomography. Because of coherence processing, it can be realized in OCT too. But about LiDAR, we are going to look through this idea. Thank you. Okay, any other questions? Okay, thank you very much for your attention. And now we come to the next